Okay, great. Well, first of all, let me say thanks to the organizers for staying on. I'm really delighted to be here. And I want to spend the next 30 minutes focusing on a little bit of what John alluded to in terms of driving new innovation, as much as it's done ultimately from materials design. Let me get this straight here. And materials discovery. And so today I want to spend my 30 minutes talking about a new tool. A new tool come along that I think has the ability to completely change the way we think about discovering new materials. So when you think about making new materials, and really what's possible. And I like to motivate this by thinking about the impact of materials on civilization. For this audience, I don't have to argue very long. It's been a good argument. And if we look from the beginning of time, entire ages have been defined by new materials, whether we're talking about the Stone Age, the Bronze Age, the Iron Age, the modern superalloy age, or we just heard even the Silicon Age. And so, although society depends so heavily on the discovery of new materials, if you are critical and look at the pace of discovery, I think you have to conclude that we're still pretty much pikers in doing this. We look around, there's tremendous technology because of materials discovery, but as scientists from the beginning of time, we've discovered and characterized less than 100,000 new materials. Now think of the number of possibilities. You look at the periodic table, the number of elements, just thinking about combinations of the reasonable metals that you could include in a material, limit to 4, and you've got millions of possibilities. Now drop that limitation, throw in stoichiometry, throw in the scale, and the fact that if we take a given material of fixed composition and reduce it in size to a certain length scale, it is a fundamentally new material. This is a really daunting problem. So I would argue that things have to change. We have to come up with a way of doing this a lot faster if we want to make meaningful progress. And so today I want to introduce a new concept, a concept that we've been working on now for about a decade. That's the concept of megalibraries. The idea that if you can synthesize materials on a tiny scale, you have two advantages. One is you can pack in more features per unit area. So a megalibrary means a library which is a million or more features. I'm going to show you some libraries where we've made as large as 5 billion features. So orders of magnitude more new materials than we cumulatively made today. And also ways of actually getting the information out and finding which of those structures are worth pursuing. But the other advantage, of course, here is that if I can go small, I can also take advantage of the fact that I can identify new materials just based upon size. So those are two really big advantages. Go beyond what we thought about maybe historically. Some of you might be familiar with CIMICs. This idea of high throughput material synthesis isn't new. But being able to go small in this space and being able to access these types of structures is. That capability comes from the invention of some tools that we've been working on now for about 25 years. I think many of you know, I mentioned in the introduction, we were involved in the invention of dip pen nanolithography. That was a really enabling tool from a research standpoint because it was the first time anybody thought about directly transporting molecules from a tip to a surface in an AAAFM experiment where you could control locally the chemistry of an underlying substrate. It's a synthesis tool. It allowed you to make structures locally, at least within the field of view of an AAAFM. And lots of folks adopted that type of technique and used it for research purposes for many different ideas. In parallel, at Harvard, George Whitesides, of course, was working on tools like contact printing. We heard a little bit about those even in the previous talk. Those tools are also quite powerful. Good for research purposes primarily. They allow you to effectively use microfabrication techniques to make a stamp, coat that elastomeric stamp with molecules, and then directly transfer that pattern to the underlying substrate. Can't go nearly as small as you can with a dip pen, but you can do large areas. So these tools are actually not competitive, they're highly complementary. They have strengths and they both have weaknesses. So in 2008, we began to think about this in a new way. We said maybe what we could do is merge these two concepts, get the benefits of both, and in the process eliminate some of the weaknesses. And that was the birth of what we call cantilever-free scanning lithography, or polymer pen lithography in its first embodiment. The basic idea was that you could make an elastomeric stamp, but not out of a pattern that you wanted to transfer, but out of appearance. And those pyramids then, like an AFM tip, could become point sources that locally deliver chemicals to an underlying substrate. But I can make these very, very large, and if I mounted them on a glass substrate or a solid transparent substrate, I could create a system that could be aligned over very large areas and have a lot of tiny little fingers that effectively allow you to control chemistry locally on an underlying substrate. That also led to a whole series of other architectures. I'm not going to talk about them today because of time. It really changed the way you think about doing scanning probe lithography, from very low throughput to very high throughput. Beampen, for example, basically takes these pyramids and uses them as light pipes. The backs of them are microscopically addressable. You can take a digital micromirror device and split one beam of light into 22,000 beams of light. And I can independently dance that light off the back of these pyramids, squeeze it through the tips, and develop anything photosensitive on the other side. That gives me independent tip control. Lots of interesting things you can do there as well. So let me introduce you to polymer pen lithography and then talk about how I think it's going to impact some of the things that actually John talked about, many of the things that John talked about, but also enable this whole new way of thinking about synthesizing materials. So here's an example of the first array we made. This is trivial to do, effectively low-end microfabrication. You put dots on silicon with the resist around them. You use KOH to do all the work for you. It anisotropically etches and creates pyramidal pits. Pour in your elastomer of interest, PDMS for example, cure, with a glass slide in the back, pull it off, or a silicon wafer in this particular case. And here you can see an array of 11 billion of these pyramids, all almost identical to one another. Comes down to 60 nanometer radius of curvature. That's what allows you to really exceed, for example, the resolution of conventional contact printing types of experiments. Put this in an AFM after it's been coated with molecules, in this case mercaptone decanoic acid, bring it down 4 times, and now in a matter of seconds you're making millions, 44 million features across many square centimeters with sub-100 nanometer resolution. That was pretty neat. So nobody had ever done anything like that with any sort of scanning protocol prior to this. Then the guys that were involved with this, 2 Chinese students, one named Feng Wei Hao and another Zijin Zhang, both of whom are professors, one in China and one in Hong Kong now, then came to me with this experiment, which I thought was pretty spectacular. They were really excited, of course, about the Beijing Olympics. And they took this array, a smaller version of 15,000 tips, and they made the logo, right, with the runner, and you can see the Beijing 2008 here. And there were a couple things that were striking about this. One was the quality of it. This was literally the second experiment that we still have in the lab. You're looking at this after patterning on gold, and we've etched it using the molecules, the one molecular layer as an etch resist, and you're seeing the raised features that are left behind. But the other thing that was amazing is that the resolution. This was done at sub-100 nanometer, 90 nanometer resolution. This was done at 600 nanometer resolution. And that's a very tough thing to do in a conventional dip pen type of experiment. In dip pen, if you want to make tiny features, you work with really sharp tips. If you want to make large features, you use blunt tips. You don't go back and forth across length scales. Here they're spanning the centimeter, micrometer, and millimeter length scale all with one tool. Very unusual. How does it actually happen? Well, it turns out that it's a remarkably forgiving technique. If you think about this, leveling is critical. You have to be level, because if you're not level, you can tip the array, and these tips will hit first, and these guys won't, and then also sort of gradient in the middle. I'll come back to that concept in a second. But what we found was this architecture is really quite critical in the sense that the initial contact force is absorbed by the base of the array, kind of like a gel pad in your shoe. It allows you to get all the tips in contact before they start deforming. And then as you uniformly press, you can see feature size here increases in size. So the other way to look at it is if I bring this down and make dots on the silicon or dots on gold, you can see that these are, again, MHA dots on gold. Tiny little features here that are circular when I lightly touch, and then square-like features as I press harder and harder. I'm effectively taking a deeper and deeper slice of the pyramid. It's a springy material. It'll go back and forth. It's completely reversible and very tailorable. It has a dip pen characteristic. The way you control feature size of the dip pen is by diffusion, letting the molecules diffuse from the tip to the surface. And we can do that as well. We use this to control feature size with tremendous precision, you'll see in a little bit. Okay, so it isn't just a tool for patterning small molecules like alkane thiols. You can pattern anything you like, anything that will flow from tip to surface. Here's an example of making fiber napkin patterns, and the first idea that we can begin to build massive libraries of structures. And what we're doing in this case is putting down a lot of different libraries that differ in the size and shape of the features, which are subcellular in size. in this case fibronectin, to control how cells, fibroblasts, adhere to the underlying pattern. And what you can see is the cells not only adopt the shape of the pattern, but look carefully. This has never been done before. Underneath the cell, with these subcellular features, we are literally controlling how the cytoskeleton forms, how the cell builds its cytoskeleton. So when you talk about interfacing cellular systems with electronics or any other type of structure, this type of capability is going to be quite critical. Let me show you how powerful it is. If you look at this, here's an example where we've got a square array, and we've got a square array here where we just put 45-degree angles lines. You can see again the cell adopting the shape in both cases, but the cytoskeleton is very differently being built just simply by putting those lines and imposing directionality. This is not a one-off type of thing. You can see circular patterns. In this case, these are stem cells, mesenchymal stem cells. Circular pattern here, we put an 18-degree radial period within this type of structure. And look at what happens. This guy here forms this type of radial cytoskeleton. You can see the lines going towards these fibronectin patch areas. You don't see that up here. You say, why do I care? In this case, this guy will become predominantly a fat cell, and this guy just becomes a bone cell. You change in contractility based upon the subcellular cues that you're providing to the cell. So we think this is going to be a very powerful way of studying cellular systems, controlling cellular systems, regardless of what you want to do. And this is just talking about one chemical cue. As you're going to see, you're going to be able to introduce many different types of chemical cues on the subcellular scale as well. Okay, what about synthesis? Well, just to fast track, this award is a little bit about technology. We also do a lot of commercialization. This is now a commercial tool sold by a company called TerraPrint. Everything I've talked about can be done with a tool that has basically disposable arrays, as many as 160,000 tips. 22,000 of them can be independently addressable with the light source that I talked about. And much of the data I'm going to show you from this point on are collected with these types of instruments. These are now going all over the world, heavily being taken up in places like China and also parts of the U.S. as well, primarily because there's a lot of building and infrastructure going on there. Okay, how are we going to synthesize? We want to introduce the concept of what I call a nanoreactor. The idea that we can control chemistry very locally by using these tips to deposit where reactions can ultimately take place. How are we going to do that? Well, reactors, oftentimes nanoreactors, are referred to as structures in solution that sequester a certain number of reactants, let's say a dendrimer, and then confine the reaction within that particular architecture. And that's one form of nanoreactor. The nanoreactor I'm talking about is where we take a block copolymer, one like the one shown here, polyethylene oxide polyethylene, load it up with metal in it, any metal salt as you're going to see, and then we disperse it in the form of micelles, use that as an ink, coat it on tips, and then we take the tips, either an AFM tip or a Bulmer pen array, and deposit features onto an underlying substrate. If that's hydrophobic, so we can control the type of substrate we use, it will beat up in the form of a reactor that literally has attoliters for less of volume. And then we can treat under reducing conditions, either plasma or heating, as you're going to see under a hydrogen atmosphere at high temperatures. Blow away the polymer, reduce the metal lines, and if everything works well, all the atoms will come together and form one nanoparticle. And here you can see that's exactly what happens in the case of gold. I generate, in this case, reactors that vary in size, in this case diameter, from 160 nanometers up to about 220 nanometers. Down here, the particles that I get, one particle per reactor is a single crystal of gold. And you can see roughly 17 nanometers up to about 22 nanometers. So roughly about a tenth the size of the reactor. Everything you put in a reactor goes into the particle. That's kind of an interesting observation. It didn't necessarily have to be the case, but that turns out to be the case, and that turns out to be quite useful. This is massively parallel. So now we can make millions using the PPL array, in this case all designed to be sub 10 nanometer in size. We can go with very, very small, as you're going to see. 4.8 plus or minus a tenth of a nanometer. For those of you up front, you can see a little bright spot here. These are the particles that form in each of the reactors. Okay, so all the atoms, again, going and forming the particles. I would argue this is more controllable than solution phase syntheses, and our group's developed some of the best solution phase syntheses for gold-based nanoparticles. So I think I can say that reliably. It's very difficult to get this type of monodispersion in any solution-based synthesis on the scale. I keep telling you that everything within the reactor goes into forming one particle. Well, if that's true, you then can begin to think about using this as a tool to understand how particles form. Because when you put an electron beam and kind of treat that as a reactor, it's kind of an interesting reactor where all the reactants are going to go into forming one product. And I can map that process as a function of temperature of the electron beam. So I'm going to show you the birth, growth, and ultimate life of a gold nanoparticle. And you can watch the process take place. The nuclei form, they begin to merge, coalescence takes place, and at the end of the movie here you see the one nanocluster that forms. That's kind of a neat movie, but there's information there. I can take that down and look at the different frames, frame by frame, going from nucleation and growth all the way to final coalescence. And what you find is two processes are occurring. One is oswald ripening, right, where one particle is basically dissolving and feeding atoms to other particles. And the other is where coalescence is taking place and the particles are merging. If you study these, you can convince yourself that coalescence is observed as the dominant process for particles or nuclei that are closer than 5 nanometers apart. Further than 5 nanometers apart, the oswald ripening mechanism dominates. So one of the things that you get is the ability to study nanocluster synthesis in a really unique way. In a way where you can set up the conditions, dial them in, and drive the process based upon. Now, we got really excited. We said, we're going to go across the periodic table, we're going to make everything. And everybody knows how this works. Nothing else works. By that, I mean we take platinum salts, we go through this process, ramp up the temperature, boom, we get a bunch of platinum nuclei. They do not coalesce and form one particle per reactor. That happens over and over and over again. So I have another very talented student, Will Young, is now a professor at Virginia Tech, take a look at this and try to understand what's going on in the reactor. And it turns out there are many things that are going on, but a couple of key things that can enable synthetic design. One is that in the early stages of heating these reactors, you drive out water, and that ultimately causes precipitation of the salt. We were, of course, just ramping right to the gold particles in the first experiments that I showed. But what we found is that if we slowed this process down, we could cause the salt to precipitate, get everything closer together. Now, lower the activation barrier for coalescence, raise the temperature, blow away the polymer, reduce the metal ion, and ultimately lead to individual particles. When you do that protocol, you now can begin to make almost anything. Gold, silver, platinum, palladium, iron oxide, cobalt oxide, nickel oxide, copper oxide as examples. And again, in mass. Whatever you put in the polymer ends up in the reactor. You can see this, and that's critical if we want to do what I'm talking about with respect to megalibraries. So here's an alloy particle, a heterostructure actually, that has an alloy of silver and gold and nickel on the outside. So this part is silver and gold. You're looking at EDAX, the color coding here for the elemental map. The nickel is the green region, and you can see we dialed in intentionally 20% nickel, 33%, 50%, 67%, 80%. There's a linear relationship here, and that's why I keep saying that everything we put in the reactor goes into the particle. That's kind of an interesting consequence here. And you can see we intentionally kept the gold to silver ratio 1-to-1 throughout the different particles that were made. Here's an example of being able to study what goes on. For example, a reactor with respect to more complex systems. The alloys, how does that silver gold alloy form? Well, we can study that because we can set the reaction up 1-to-1, silver ion to gold ion within the reactor, and then we can map it. And what you find is gold will always precipitate first. You form the gold particle, and then silver wets, and then ultimately diffuses into the gold. You can very clearly see that in the time-elapsed EDAX type studies. So the gold particle always becomes the first product, the kinetic product, and then the silver is wetting the surface and ultimately diffusing through them. That's why I say I think this is going to be extremely informative in terms of understanding how complex systems form. Here's an example of how complex can be. Peng Shen in my group, very, very talented student. Sounds like I only hire Chinese students. There are a lot of talented Chinese students. He took every combination of 7 elements, built this massive library. Most of these particles have never been on the planet before. How would you make a 7-element type particle? You probably could if you're a great synthetic chemist like Mirkin, but you'd have to spend a lot of time trying to work out the conditions. Here, because of what you put in the reactor, you know it's going to go to one product. You can actually systematically look at compositional space in really fantastic ways. And what you see in this case is a couple of things. One is they all can be made. They're all the same size and have been made to be the same size. But he went through and characterized all the phase behavior here and the interfaces that form. Nobody knows how these types of structures are going to behave. Well, we can do that. And if you're interested in this, we actually went through the full analysis. And you can begin to create design rules for making these types of polyelemental systems, where you can design interfaces, both the number of interfaces, the types of interfaces. You can dictate it by an understanding of interfacial energies. And as you begin to study the hierarchy, going from 2-phase, 3-phase, 4-phase, 5-phase, or 2-element, 3-element, 4-element, 5-element type systems, you can begin to create rules that allow you to predict what the next set of structures will do. And so I think there's going to be incredible value added in terms of fundamental understanding with respect to polyelemental systems that come from these tools. How low can you go? So this is, I got a great thing about Johnson doing work. That's absolutely true. You go grouping, you can make all sorts of grandiose challenges and statements and go home and relax, and the students then go figure out how to make it happen. That's kind of what happens here. So I said, in principle, we should be able to go down to a single atom. We should be able to reduce the number of metal atoms, and then ultimately get an atom and know where that atom is, and 2 atoms, and 3 atoms, and 4 atoms, and 5 atoms. Well, it's a little more difficult than it sounds, because as you start diluting, you run into a big sampling problem, right? And so you get a stochastic mess. So again, these guys figured out that what we could do is effectively synthesize polymers and use end capping now to make the reactor effectively primarily polymer and reduce the number of metal content in a highly controllable way. Porphins are wonderful because I can put in all sorts of different types of metals. Big question was, would these then ultimately convert like the other types of materials into the nanoparticles, single reactor, single particle? And you can see that exactly what happens here. Where we're dialing in, and these are really tiny reactors now, 60 nanometers going down to less than 20 nanometers. If you look at this, we can synthesize particles from 1 to 5 nanometers. So when we're less than a 30 nanometer diameter nanoreactor, we can make sub 2 nanometer particles. We're getting down to a countable number of atoms. Well, I took it out, it was real good. You're literally your yoctoliters of volume in the reactor. These are really, really tiny controlled systems. And here you can see we can then take these polymers that are end capped and we can now begin to mix them, right? So that we can build these tiny particles, platinum, copper, platinum, nickel, platinum, copper, nickel. So we can begin to play that game as well. So we're not there yet, but I believe we're going to get there. And I think this is going to open up a whole new area. It's going to be very important in many fields, especially in catalysis. What about catalysis? Can I build libraries and discover new catalytically active systems, new materials that have unusual optical properties? I think the answer is probably yes, but we have to do a couple of things to get there. The first is this. We spent all this time trying to level. We said, hey, wait a second, what if we miss a line? We can, in one shot, build a library of structures that systematically vary in size. If those are all reactors, that's going to give us particles that vary in size. I then can take and spray different types of polymers, the precursors, onto the tips in gradients. And now I can systematically build arrays that vary both in size and composition. And then, in principle, the setting off the races. Well, this is exciting, but when we've got a lot of skeptics at Northwestern, and one of my students is going through a second-year oral exam, and one of the great catalysis people starts challenging him. Peter's there, and of course, get a little defensive too. And he says, well, these are beautiful, Chad. They're wonderful particles. They're too big. But turns out I don't think it's true. 2 is, how do you know the catalytically active? They might be poisoned with carbons. That's true. So the first thing we did is we said, let's go find a catalyst that we already know is a working catalyst. If we get confidence there, then we can go and more confidently look for unknowns. So in this particular experiment, we're looking at this particular hydrogenation reaction. It's known that gold and palladium particles made via solution methods are better than gold and palladium alone, pure gold and palladium particles. Well, we can synthesize those, I think I convinced you of that, and then we can study that process. And if you're looking at both conversion or turnover number, you can see very clearly that the gold and palladium outdoes the monometallic systems, confirming what the literature has suggested. So now we can begin to think about discovering unknowns. Well, there are a variety of ways you can do that. One is you can reduce the field of possibilities by working with theoreticians and saying, what might be a good target? The other is just to go to the full Megalibrary approach. I'll give you one example of each. So here's an example. Remember, you have to have a way of getting the information out. You have to have a way of driving reactions. It's not just about making the particles. So we can also pattern on electrodes. glassy carbon electrodes in this case, and we can build libraries of particles for many of the same particles and look at the behavior of one particle at a time, but many times over. And so in this case, we're going to look at it in the context of the HER reaction, hydrogen evolution reaction. So we went to Chris Wolverton, a great theoretician at Northwestern, and asked, can you look at the different types of metal possibilities, structures that hadn't been made before, and tell us what might be good in terms of the HER reaction. And then we can synthesize in a nanoscale form. We can only do it in bulk scale form, but we can synthesize in nanoscale form and see if they actually map or where they deviate. And so you put this volcano plot together, looking at the hydrogen affinity, and you can see very clearly platinum, which is what you're trying to beat, that's king, way up here. And the single element systems here, some of the 2 and 3 component here. Look at these 2 guys up here. They're up there, and they, in principle, should be better. Well, we can make all those particles, and we did. And then we studied them, and we look at them and compare them to platinum. So this is the overpotential, and you can see platinum copper here, lousy, platinum nickel, lousy, platinum gold, lousy. Here's one of them, lousy. That was a shocker. Then you look at this guy, platinum gold copper. It's comparable to platinum, but it has 1/7 the amount of platinum. It's actually a record now in terms of the best HER catalyst out there. So that tells you, yes, you can discover new types of catalysts, but I want to point to something really important. The great thing about this isn't just finding things. You actually can study things before, during, and after. So why was this one bad and this one was good? Was it that Wolverton just isn't that good in terms of the theory, I oversold him? Or is there a better scientific reason for it? Turns out the latter is the case, thank God. If I look at platinum, gold, and copper, it's exactly what he modeled, an alloy. That's what we told him, right? You look over here, platinum, gold, nickel, you can tell in the index, the phase separates. It's actually platinum, gold in one phase and nickel in the other phase. Well, that makes sense, because we know platinum and gold's lousy, and we know nickel's lousy. So it's the fact that we got the alloy type structure here that we actually got the catalytically active one that works in this case. And so this ability to actually go back and cross-correlate structure with property and function, I think, is also important, because everything fits. Very difficult to do in solution. Okay, last one is how you build libraries now where you can begin to search space. Here we collaborated with the Air Force, Megalibraries, and his team at Wright-Patterson, because they have a good screening tool. They have this airways detector, which is basically a Raman system that has a whole series of posts that we can pattern different types of materials on. And they can probe with a scanning Raman and look, in this case, for signatures for single-walled carbon nanotube. And they were interested in trying to identify new catalysts that would facilitate that transformation. And you can see very clearly in this case when we look at gradients on these pillars that systematically vary at the 2% level, both in terms of composition and size from 2 nanometers up to, I think, 20 or 30 nanometers. Enormous numbers of particles, literally over 5 billion particles screened in one experiment. We then can begin to get maps like the one shown here. And what we found in this particular case was a new catalyst, a single carbon nanotube, one that nobody had known about before. Gold, 3, copper, 1. Clear maximum. Again, an example of how you can screen these types of libraries and rapidly get out the information and then spend the bulk of your time on it. Both in this case and the previous case with the HER, we then go back and we then synthesize them via the long and hard routes. But the point is we know which ones are worth making after we go through this particular process. And we try to confirm or not that the materials made by bulk solution synthesis mimic the properties of what we found in these types of systems. Okay, so I'll just finish with this then. We got started in this because we were thinking about things like molecular electronics. We were thinking about things like enabling nanoelectronics early on with the invention and development of DIP. But I think what's really important is 2 transitions. One, moving away from AFMs to these cantilever-free printing tools. That is really a big deal because most of the time when people show you something made by scanning protolithography, it's been magnified up to 1,000 times. You can't physically even see it. Here you can make structures that you typically associate with high-end microelectronics and nanoelectronic type techniques. But in addition, what these tools do is they open up a new domain in synthesis. The ability to locally control chemistry, study reactions within these types of reactors in a very deep way, and to make materials faster than I think we've ever seen before. And I think that bodes well for using them to ultimately discover all sorts of new structures that have unusual properties that can impact many areas. Let me finish by acknowledging the folks that have done the work. This is the group at Northwestern. I mentioned most of these guys throughout. I do want to mention two people. They're fantastic. One was just an undergrad member, Jared Maglin, and Dr. Andre Plunkin. They took the original tools of polymer lithography, AFM, a lot of optics, all kludged together. Very complicated, about 3 times the size of this desk. And they built that system that I showed you, which is just an unbelievable system. Wrote all the software, and now they are going around selling and distributing it all over the world. And it's kind of a neat thing to see it go from just kind of crude concept, but ultimately commercial product. And the funding then was provided by these groups, very heavily by the Air Force and the DARPA through their tip-based application program, and most recently through the Sherman Fairchild Foundation. Stop there, and thank you for this great honor, and I'd be happy to answer any questions.
Thanks for building libraries of materials. Any questions from the audience?
So I think it's a very exciting and very extraordinary things being done. I just had a small question on that cooperativity and self-sorting. Self-sorting and cooperativity. Okay. Are these particles following the principles? Self-sorting and cooperativity.
What do you mean by self-sorting?
Self-sorting, so you have got certain cases that okay, the two metals, they are just coming together, not together. Okay, some of them are coming together.
No, the point is they all come together. So if I take a reactor that has silver salt and gold salt in a 1-to-1 ratio, I will get a particle in that reactor that has 1-to-1 silver 0 and gold 0. Same thing with copper and all the other elements as well. That's the really neat thing about it. It basically is taking everything that you put in that reactor, which you define ahead of time, with the way you prepare the polymers. You deposit it. And then every atom is forced within that reactor to come together. The reason I say it's kind of interesting is it could have been that we had many different atoms. We could take the 7 element systems. We could have had 3 or 4 different particles that all just kind of broke apart. But the process actually forms these structures that are multiphasic, have well-defined interfaces, and I think because of that are going to be have unusual properties.
Well, while I was observing, I was seeing that towards my left side, it was the cooperativity.
What were you showing?
Toward the left side of the table, you have shown a table. Toward the left side, they are cooperative operating, and other side is self-sorting operating.
I'm not sure I understand. You're going to do it. I don't know.
In your table, I was thinking that this side, the principal cooperativity between the metal is operating, and other side is self-sorting because they just separated out.
No,
When they are normally, okay, see they.
Oh, okay. So I think I understand what you're saying. So with the particles that have this multiphasic behavior, like this type of thing on the right. Yeah. Well, that's you have to scan, right? So the one thing you can't control is the particle orientation. So we're making many of these at once, so he can go through and look at them and say, hey, they're all one particle. But they all don't look like that because they can rotate this way and this way, right? So these are presented in a way so you can very clearly see the domains that define, in this case, the platinum, gold, and the nickel. But that comes through a lot of systematic analysis of the structures and then picking ones that we can show the multiphasic characteristic of it. They're not all forming in that particular orientation with one material to the right and the other materials to the left.
Let's take one more question.
I have a question in the catalytic conversion of nitrophenol to aminophenol. There are large number of nanoparticles known for converting nitrophenol to aminophenol. What is the specialty of nanoparticle?
What's what?
There are a large number of nanoparticles known which can convert nitrophenol to aminophenol.
Yeah, no, that's
about
not
90%.
Yeah,
What is the specialty of the nanoparticle?
that's not the exciting part of it. So the point of that experiment was just to actually do what you were saying, which is to prove that we can make particles that are catalytically reactive and do what all these other people have said can be catalyzed. Once we know that, we know we have catalytic nanoparticles, and that's what opened up the ability to go after the unknown systems, the HER reaction and the other catalysts. So there's no big deal about the particles that affect the hydrogenation reaction, other than the fact that they work and they mimic the properties of the bulk solution phase type particles. That was the only reason we went down that particular path, just to convince people early on that the particles made through this technique can in fact be catalytically active. That was the first step in being able to go after unknowns.
Right, thank you.